Hello everyone. Let's continue with the discussion of sets. So we started Venn diagram in last class. Let's continue Venn diagram throughout this class. We also understood or touched upon the basics of operations on set. So U stands for union. We understood that union means uniting all the elements of the sets involved. This is inverted U as intersection. Intersection is common in all the sets involved. This symbol stands for difference. Second set minus first set. Elements of second set minus first set, or first set minus common elements. The fourth one is complement. Now, if A is a set, say 1, 2, and 3 are the elements of set, then complement of set is written as A dash or A complement, and its value will be equal to U minus A, where U stands for universal set. In this question, the universal set is 1, 2, 3, 4, then the value of A complement will be 4. In short, if you unite, if you take the union of A and A complement, you will always end up with U. And if you take the intersection of A and A complement, you'll always get phi, a null set, because there would be nothing common between A and its complement, or A set and its complement. Now, here, in this particular example, U is a universal set, A and B are two sets with a little portion overlapping between them. Now, this portion that is overlapping between them is called intersection. It is a common region. Any element present in this region will be considered present in both the sets A and B. So this shaded region is called as A intersection B. In the second figure, let's shade this complete region. Now, what are we shading over here? We are shading portions of A as well as B, including the intersection part. That means A union B. The shaded region is A union B. If we shade only part of A, excluding the part which is common between A and B. So here you're taking a set A and you're subtracting every element of B from it. Hence, it is A minus B. Now, the same value can also be written as A intersection B complement. How? How is it possible? So let me show you in this particular figure. A can be written as this region. This pink region is all A. Any element in this region will be considered as part of A. And B complement is the green region. Anything which is not present in B. So you have a circle describing B. Excluding the circle, everything which is not in B will be considered as B complement. So the green part is B complement and the pink part is A. You're taking the common region in these two regions. So what is common in these two regions? Let's denote it by red. This part is common in both the regions, A as well as B complement. Hence, the same figure A minus B in the initial figure can be called as A intersection B complement. Now, here in this figure, A and B have nothing in common with each other. That means no element of A is present in B. So, A and B are called disjoint sets. Disjoint sets means A intersection B will be equals to phi. with this information, we stated that A and A complement is equals to phi, which means we can also say that A and A dash are disjoint sets. Next, let's consider another universal set U and A and B as true sets in it. If I shade up the region from B part, which is not present in A part, then similar to the previous question, it can be written as B minus A, because you're removing all the elements of A from B. This can also be written as B intersection A complement. Here, this particular shaded region is present in B as well as in A complement, and it's a common region between both. The explanation is same as the explanation for A minus B. Next, what if we shade this particular region, part of A and part of B? What are we doing? We are uniting two regions, but we are uniting those elements which are present in only one of the sets. So you can write this as A minus B, which is the explanation for the first shaded region on the A part, united with B minus A. Or you can also write this as A intersection B dash united with B intersection A dash, uniting these two regions. Or by basic observation, you can also write this as A union B minus A intersection B. A union B means the whole part. I'm using yellow to describe it. A union B means this part, the intersection part, and the B part. Now from this particular part, you're removing the middle part, intersection part. You're left with regions where elements are present only in one set. Next, let's say we shade this particular region. The outside region, or we are considering all the elements which are not present in either of the two sets A and B. That means we are taking the complement of A union B. This means A union B, its complement, because U minus this region. When we are shading a region, it means that we are considering all the elements present in that particular region. By shaded region means considering elements present in that region. If we shade anything except for A, so anything except for A will be this part. So it can be written as A dash. Similarly, B dash can be written as anything except for B. Sorry. So all the complete region beyond B, complete region which is not present in B. For A intersection B complement, it would be any region except for A intersection B part. Let's consider this, a set of a system, a question which contains 3 sets A, B, and C, or Venn diagram using 3 sets A and B and C. Here also you'll have multiple regions. Let's consider this region first. Now, this region has only those elements which are present in A. So, from A, from the set A, you are removing B and C. Okay, from set A, you're removing B and C. Or from set A, you're removing this part. Amongst A, from the boundary of A, you have to remove, let's use pink. You have to remove this region, and this region. So either you can subtract these regions, or you can write it as A intersection B complement intersection C complement. How did we come up with this answer? So if you consider A, let me use the second figure to describe how we came up with this answer. This is my A region with yellow. All the elements in yellow will be part of A. All the area in green will be part of B complement. The second part is B complement. So B complement is any region which is not present in B. That means the whole union part outside the 3 circles and the whole A part except for the B part. This region and this region. The green part is your B region. And A region was denoted by yellow. What is C region now? How will you describe C region? We need C complement. So anything which is not present in C. This region is not present in C. This one, and the whole union part, this one. All this region is not present in C. What is common in all these regions? This region is common in all these regions. And this is the required region. In the previous figure, this is the required region. So this is how if you take the intersection of A, B complement and C complement, we end up with only that region which contains elements present in only set A and not in B or C. Now, if we have to reciprocate the same thing for B, that means we want elements present in only B and not in A or C, then how will we do so? We need this shaded region. Elements present only in B and not in A, B, or C. So this would be B intersection A complement intersection C complement. So you have to take the complements of those sets which are not involved. A and C here are not involved, hence A complement and B complement, and intersection of all 3. If you have to consider only this region, that means elements of sets which are present, elements which are of only set C, not common with A or B, then it is C intersection A complement intersection B complement. Let's find some other examples. Let's see if we want the value of this region, a region which is common for A, B, and C. So this can be easily written as A intersection B intersection C. Understand, we'll have only those elements which are present in all 3, not 2 of them, but all 3. If you want elements present in this region, by observation, we know that here, this complete boundary, this leaf-like structure, contains elements from A and B. So this leaf-like boundary contains elements of A and B. So by default, it is A intersection B. In the second part, A intersection C. Third part, B intersection C. What if we consider two of these leaf structures in one go? Then what does it mean? It means both if you can observe, both the regions are present in the circle of B. Okay? And both the regions taken combined is present in A union C. This complete region is present in A union C, and the complete region is also present in B. It is the intersected part, it is the common part between A and A intersection A union C. Let's understand this a little bit in detail. The same part. We are shading the same region, and we require this region. Now, based on our explanation, we have said this is the answer. B intersection A union C. For this shaded region. How did we come up with this answer? Let's consider A union C. A union C means this whole region. What does B mean? B means this whole region, this part, this part, this part, and this part. Now, which region is common? Let's delete the uncommon region. This region is not common. Sorry. Instead of deleting, let me use the red to highlight the common region. This region is common, this region is common, and this region is common, which is the required region. Hence, the required region has the value of B intersection A union C. We can also describe the same in a different fashion. We can consider the addition of A intersection B and B intersection C. Now, A intersection B would be this region. A intersection B. In this, you can unite B intersection C. In this, you can unite B intersection C. Now, if you can observe these two values, they both are equal. You came up with the same shaded region. You came up with two explanations for the same shaded region. If you can also observe, this looks something like a distributive property. Now we can write this as B intersection A union B intersection C. If you write A intersection B or B intersection A, it has the same meaning. Intersection is commutative in nature, as we studied earlier. In both these values, these brackets, B intersection, this part is common, B intersection, B intersection. So what we'll do is, we'll take this common, B intersection. In bracket, what is left? B intersection A is left, U, this part, B intersection is taken common outside, and then you are left with C, which is this particular value. This is distributive property. It's called distributive property. So let's write this explained form in the previous slide. This value can also be written as B intersection A union B intersection C. You're using distributive property. Now, let's do some other problems, some other shaded regions. Now, instead of shading these regions, let's see what we get if we shade this region and this region. In this part, if you can observe, you have A intersection C and B intersection C. Now let's do it with distributive property, but in the reverse fashion. So it is A intersection B united with B intersection C. In both these values, you have just a second. Sorry, I made a mistake. It is A intersection C. Yeah. So A intersection C united with B intersection C. In both these values, C intersection is common. So C intersection with A union. Also, how did we come up with this explanation? We considered this region in addition to this region. We're not adding per se, but we are uniting them. We're using the union of both the sets. Because the set values are not added, they are just merged. So that's uniting them. C intersection A union B. With this explanation, we can also understand that whole region is common between C, the circle of C, and between A union B. Okay. Moving on to the next, the last section, shaded region, which we'll have in the same type of question is this region. So this region means A intersection with B union C, or A intersection B union A intersection C. If any of this is not understood, you can comment it. You can write it in comments, and I can re-explain it to you in either another video or in the comments itself. Let's consider this region, and this region. Now, what you're doing, you're considering all the three regions, and then you're removing the region which is common for all the three sets. So one lengthy way of writing this is A intersection B union A intersection C union B intersection C, and then you're removing A intersection B intersection C from it. And this looks a little bit tedious. Okay, so to come up with this particular part, let's understand these three parts separately. Let's see if we can come up with another explanation for it. So let me consider first part. First part is this region. That means you're removing the intersection, the region with the intersection of 3 from A intersection B. A intersection B. So which region is A intersection B? The whole region, this part. From this part, you're removing the lower part to get the required region. So A intersection B minus A intersection B intersection C. You're removing this from it. How else can you write the same thing? This is equals to A intersection B intersection C complement. Let's understand this in this figure. A intersection B would be, I've named it differently. Hold on. This is A intersection B. From this, you are removing this particular part, A intersection B intersection C, or this part common with C complement. What is C complement? Anything but C. So I'm shading it with yellow. Anything but C is this particular part. What is common amongst these? The region that is required. This region is common, which is the required region. So this is A intersection B intersection C. Now, this is a simplified way to do so. That means apart from getting into the details of subtraction and writing too many sets, union and intersection too many sets, you're trying to make your things concise. You're trying to make your observations concise. The more systematic way you think, the better you'll understand, or the smarter way in which you'll understand. Let's consider another region. This particular part. Now, this part is present in B intersection C in this leaf. And from this leaf, you have to remove all the C part. You do not need any of the C part. Okay? Sorry, you do not need any of the A part. The circle is A part. So, B intersection C may say you're removing C part. You're removing A part. Or B intersection C intersection A. Complement. Complement is when you do not require that particular set, when you do not require the elements of that particular set. Then that is when you take a complement. What if you consider the third region, this particular region? What is this region? A intersection C, all the elements in present this, intersection B complement. Okay, hope this is understood. Let's combine the three regions. So by default, you'll have to unite the three values. So you'll end up with A intersection B intersection C dash union A intersection B dash intersection C union A dash intersection B intersection C. Okay. What if we shade the whole regions? These three regions. This was fairly simple, right? So you're considering A intersection B union B intersection C union C intersection A. Intersection B would be this leaf. B intersection C would be this particular part. A intersection B is this part. B intersection C is this part. And A intersection C is this part. So anything in here, or in here has been united. So next is, let's consider if you want this region and this region. So now it becomes fairly simple. It is A and you're subtracting C from it. You don't care whether it's in B or not. B is irrelevant for us. From the circle of A, you need no elements which are present in C. Or it can be written as A intersection C complement. So with this, you can also come up with, you can consider this as a formula. This can be considered as a formula. It's useful in solving, improving certain properties in sets. Some type of questions which are present in the miscellaneous exercise of ncert. Similarly, you can we can shade other regions in the same manner. If you consider B part, if you shade this part, that means from B you have to remove every element which is present in A. You don't care whether C is present or not. So from B you are subtracting all the elements of A. That means B intersection A complement. Even if it is in 3, the value remains same. C is irrelevant for us in this particular question. If you have certain region over here, which is A intersection B complement, and then you can unite this with B intersection C intersection A complement. Any combination of these regions, how many regions do we have? 1, 2, 3, 4, 5, 6, and 7. And if you consider this as 8, so any of a combination of these 8 regions will be asked or can be drawn. If you can draw any, if you can find the value of any of these regions, then you excel in Venn diagrams. So we'll stop here and we'll continue other types of Venn diagrams and certain properties of sets in the next class. Thank you.